Hello friends, in the previous video we have completed the introductory part of the solutions. Now here mainly you have to remember one thing, that we are discussing binary solutions for this current year, and in this we have solid in liquid and gas in liquid. We have to discuss this type of the solution in detail. So here first we have studied that what is solute, what is solution, etc, etc, how we can find out the concentration of the solution, etc. Now depending upon the capacity of the solute dissolved in the solution, we have three type of the solutions: unsaturated, saturated and supersaturated. If added solute dissolves in a given solution, then that particular solution is called as an unsaturated solution. That if you are adding if you have just prepared a solution of 5 ml salt water, and if you are adding 2 gram, 3 gram or 5 gram, and if it dissolve in that, then that type of the solution is called as unsaturated. That means solute can be dissolved in that. But if we come towards the saturated solution, it's a solution in which maximum amount of the solute get dissolved. That is, simply we can say no more solute dissolve in it. No more solute dissolve in it. Now it's a solution which contains a maximum amount of the solute in the dissolved state. That means if we add excess of NaCl in the solution, and if it doesn't dissolve, then that type of the solution is called as a saturated solution. Then super saturated solution, here it's a amount of solute dissolve then its saturation point. That means if saturated solution is there, and if you are adding a solute in that, and if you are heating that one, a superheating, due to the heating a more amount of the solute get dissolved in that, that is it cross the saturation point, and such a solution is called as a super saturated solution. So it's a next stage of the saturated solution. Now after this we have solubility is nothing but amount of solute, that is a maximum amount of solute that dissolves completely in a given amount of solvent at constant temperature. It's nothing but this related with the saturated solution, that is how much amount of the solute is going to be dissolved in the given solvent. That amount is nothing but the solubility, or it's nothing but the amount per unit volume of a saturated solution. So its unit will get moles per liter. In 1 liter how much amounts of moles of solute is dissolved, that term is nothing but the solubility. Now factors affecting on solubility means what? That whenever we are discussing factor, that means due to nature of solute and solvent, whether the solubility is going to be increase or decrease, effect of temperature. If we increase the temperature, what will happen about the solubility, whether solubility increases or decreases, effect of pressure, that we have to discuss here. Now here we have one term, like dissolves like. Now here solute dissolves in a solvent, we are discussing this one, solute dissolve in a solvent. So like dissolves like, that means if solute and solvent, if they have similar type of the intermolecular force of attraction, then they can be dissolved, that solute can be easily dissolved in that. If they doesn't have, then solute cannot be dissolved in that. For example, if we say polar solute can be dissolved in polar solvent easily, or polar, even we can say ionic solute can be dissolved in an ionic solvent. For example, NaCl can be dissolved in H2O, but the same NaCl cannot be dissolved in the benzene C6H6, because C6H6 is not a polar, benzene is not a polar, it's a non-polar. In another way we can say non-polar solute can be dissolved in non-polar solvent. Non-polar solute can be dissolved in non-polar solvent. For example, if we say a naphthalene can be dissolved in C6H6. Naphthalene is a non-polar, that is, it is an organic compound. Benzene is an organic solvent, so it can be dissolved in that easily, but it doesn't dissolve in the H2. So non-polar cannot be dissolved in the polar solvent, and polar solute cannot be dissolved in the non-polar solvent. So it comes like dissolves like. So it is very important that similar nature of the solute dissolve in the similar nature of the solvent. Even if we say HCl gas, it has a higher solubility in water as compared to the O2 gas, because HCl is a polar in nature, but It's due to the similar oxygen molecule, it doesn't dissolve into the water, but its solubility in the H2O is less. O2 dissolve in the that solubility is in lesser amount as compared to the SO. Now effect of temperature in solution, we are getting two type of the reactions then when we are dissolving any substances. For example, we have KCl dissolves in the water with endothermic process, that heat is absorbed. So obviously when we provide heat to that particular solution, that means suppose if we are just in temperature is increases, then obviously solubility of such a substances or solute is increases, because it is endothermic, heat absorbing process is there. So in such a case, substance when dissolve in that particular solution, its solubility increases with increasing temperature. In opposite to that, if any substance or solute when dissolved in the exothermic process, that is evolved heat is evolved. In such a case, if we increase the temperature, if we increase the temperature, its solubility is going to be decreases. Now if you move towards gas in liquid, if we dissolve gas in a liquid, now dissolution of a gas is exothermic process. So obviously solubility solubility of a gas decreases if we increase the temperature. So it's according to Lee Chatelier principles. Endothermic process, if we increase the heat, that is if we are increasing the temperature, solubility increases by absorbing the heat. Exothermic, temperature increases, solubility decreases, so heat is evolved here. So dissolution of the gas in is exothermic process, that heat is evolved. So such a for such a solutions, solubility of the gas decreases with increasing temperature. So this again you have to remember. Then effect of pressure, as solid are incompressible, we cannot be compressed, these are incompressible, we cannot compress solid. So there is no effect of pressure on solubility of solid in liquid. There is no effect of pressure on the solubility of the solid in liquid. But as we know, there is an effect of the pressure on the gas. So if pressure above solution increases, solubility of gas increases. If pressure above the solution is increases, solubility of the gas is increases. The best example are the carbonated drinks. When we open the cap of that carbonated drinks, the gas get evolved from that, that pressure is released. And this, there is a relation, that quantitative relationship between pressure P and the solubility S is given by Henry's law. Henry's law, and the law is here. Henry's law, we can state Henry's law as we know that solubility is increases as pressure is increases. So here solubility is directly proportional to pressure. Solubility is directly proportional to pressure. So at a given temperature. So simply we can define Henry's law. Henry's law state that solubility of a gas in a liquid is directly proportional to the pressure applied above that solution, okay, at given temperature. So here we will get S is equal to KHP. KH is nothing but the Henry's constant. Here S is solubility, which units is mole per liter. P is the pressure, which units is bar. So from this expression KH will get S upon P. So S is nothing but the mole per liter and pressure is bar, so mole per liter per bar. is the unit for kh. Now here we can define the kh. If P is equal to 1 bar, then we'll get kh is equal to s. So here we can define the kh. Kh is nothing but the Henry's constant. Kh is a solubility of a gas in a liquid having pressure above solution is 1 bar. That is, if a solution carries a 1 bar pressure, then Henry's constant is nothing but the solubility of the gas in that liquid. Always remember, whenever we have to give a definition for any constant, the term which is multiplied to that constant, that we have to consider as a 1. Then here ammonia and CO2 doesn't obey the Henry's law, because their solubility is much more as compared to the Henry's law, and this is due to their reactions which are given in the textbook. You can go through from that. They react with the water, forming the particular acid and base. Application of Henry's law. Henry's laws can be used for production of carbonated drink, scuba diving. It is helium is mixed to control the pressure, and at high altitude it is used, and for the functioning of lungs. Even effect of addition of salt on a solubility of a gas. All you have observed that when we add a salt into the soda, what we add is salt, then bubbles comes from that, effervescence comes from that particular solution, and that effervescence is nothing but the evolving of the CO2. That means if we add soluble salt into the any carbonated drink, we are getting effervescence, and this effervescence indicates that a solute dissolved CO2 comes out from that solution. That means if we add more amount of solute, more effervescence we are getting. That means if we are adding a salt into the solution, its solubility decreases as CO2 released from that particular solution. Now we have next Raoult's law we have to discuss. Raoult's law gives a relation between the partial pressure of a solvent or the solute and its mole fraction. So before that we must know what is meant by partial pressure. So here I have taken a one container which contain the two gas, A1 gas having a partial pressure P1, A2 gas having a partial pressure P2. Now A1 and A2 are the gases. Now partial pressure is nothing but the pressure exerted individual gas in the mixture. Now A1 exerting some pressure on this wall of this container. Uh, so A1 has carries some pressure which is called as a partial pressure in this mixture, and its partial pressure is nothing but the individual pressure exerted by individual gas in the mixture. Now Dalton's law also we must know, it's nothing but the total pressure. Now here we are getting a total pressure of this mixture, and this total pressure is nothing but the sum of the partial pressures of the gases. If you have just taken the three gases, then we'll get the sum of the three gases, partial pressure of the three gases in that container. So P is nothing but the sum of the partial pressure of the gases in that solution. So here we'll get P is equal to P1 plus P2. Now Raoult's law, it gives a relation between partial pressure and mole fraction of substance, partial pressure of the gas and its mole fraction. Now Raoult's law, simply we can say, if we have just considered A1 and A2 are the two liquids having P1 and P2 are partial pressure with mole fraction x1 and x2 are mole fraction, then according to Raoult's law, P1 is equal to P10x1 and P2 is equal to P20x2. So according to Raoult's law, partial pressure of a component in a solution is a product of vapor pressure of the liquid in a pure state and its mole fraction. Here P2 is equal to P20x2. So partial pressure is a product, or it is equal to the vapor pressure of the pure component and its mole fraction. So here we are getting for the solvent A1, liquid A1 will get P1 is equal to P10x1, and for A2 will get P2 is equal to P20 x. Now, according to Dalton's law, we'll get P is equal to P1 plus P2. P is nothing but total vapor pressure of the mixture A1 A2. So from the above equation we'll get P10 x1 plus P20 x2. P10 x1 plus P20 x2. So P is equal to P10 1 minus x2 plus P20 x2. So P is equal to P10 minus P10 x2 plus P20 x2. So P is equal to, now here x1 plus x2 is equal to 1, so x1 is equal to 1 minus x2. Sum of the mole fractions of all the component is equal to 1. Now here x1 is in place of x1 we have substituted 1 minus x2. Now this will write down p10 p20 x2 minus p10 x2. So p is equal to simply p10 plus p20 minus p10 x2. So this expression we can write down. This expression we can write down P is equal to P20 minus P10 x2 plus P10. Here P10 and P20 are vapor pressure in pure state, which is constant, so its value is not going to be changed, but P is going to be changed, depends on the x2. Now if we compare this, so we'll get one y is equal to mx plus c. This equation looks like y is equal to mx plus c, so it's a straight line having slope m and intercept c. So if we plot a graph for this, vapor pressure versus mole fraction, will get a straight line which is nothing but the P, okay, which is nothing but the P is equal to P1 plus P2, but it's a straight line. Here we have again the two equations, P1 is equal to P10 x1 and P2 is equal to P20 x2. P1 is equal to P10 x1 and P2 is equal to P20 x2. Suppose here we'll consider x1 is equal to 0 and x1 is equal to 1 and x1 is equal to 0. Here x2 is equal to 0 and x2 is equal to 1. Now from this equation, these both equations are looks in the form of y is equal to mx. Now it's a vapor pressure, both the axes are the vapor pressure. Now x is equal to 1. If we just put x is equal to 1, then this value will get a p10. And if we put x1 is equal to 0, x1 is equal to 0 or x2 is equal to 1, x2 is equal to 1 in this equation, so we'll get p2 is equal to p20. So here we'll get p20. So if x1 is equal to 0, then p1 is 0 from this expression. So for this we'll get p2 is equal to 0, and for x2 is equal to 0, p2 is 0, so here we'll get the p10 from this expression. Now p is equal to p10 x1, as we are moving from we are moving from 0 to 1. So if we draw this line x1 is equal to 0, so we'll get p10 as we move from left to right. So this is what the origin for the p10. So this graph will gives a, this line gives a p1. And if you move from x2 is equal to 0, so this we can draw. If we connect from this, so this line is nothing but the p2. So these are what the straight line for p1 p2, and this is the intercept, that is a p is equal to p1 plus p2, and this is what intercept for the for this expression, okay, y as an intercept. Thank you.